Displayed in front of you are 25 of the 26 continuous probability distributions available in numpy, Python's backbone computing package. Sampling from any of these distributions happens in the blink of an eye. And although each is sampled using a unique process, when we boil these down, only 3 methods are used: inverse transform sampling, rejection sampling, and statistical transformations other than inverse transform sampling. But rather than think in terms of a menu of available distributions, we will find it more insightful to think in terms of an ecosystem of probability distributions. The 26th distribution that was not displayed on that menu is the standard uniform. It is produced by the PRNG or pseudo-random number generator and forms the very base of the food chain. The standard uniform serves as food for the 3 members of the next layer, 3 distributions that, along with the standard uniform, form the core of the ecosystem. These are so important and so widely used that they come in both standardized and unstandardized form. One level higher yet are a number of distributions that, like the members of the core group, feed on the standard uniform, but they also feed on the distributions that are members of the core group. Finally, at the highest level are a number of other distributions characterized by the fact that these do not directly feed on the standard uniform. Rather, they feed on members higher up in the food chain. I find the following analogy with the aquatic ecosystem remarkably fitting. The role of the standard uniform in the aquatic ecosystem is played by phytoplankton, which represents the very base of the food chain. One level higher is the zooplankton, which feed on the phytoplankton, but also on each other, and which together with the phytoplankton can be thought of as forming the core group of the aquatic ecosystem. These are the enablers of the entire ecosystem. One level higher yet are the small fish, which, like the zooplankton, feed directly on phytoplankton and on zooplankton. Finally, at the highest level are a number of large predators, which are characterized by the fact that they do not directly feed on phytoplankton. Rather, they eat zooplankton and small fish. And should the phytoplankton disappear, the entire ecosystem would come crashing down. And so it is with the distribution ecosystem. Should the supply of randomness from the PRNG dry up, the entire ecosystem of probability distributions would cease to exist. This video has a 2-part goal. The first goal is to explain how an ecosystem of probability distributions is put together. In the process, we will gain a good understanding of how the numpy ecosystem functions, but the knowledge we will gain will transcend numpy and will apply to any other language and even allow us to build our own ecosystem. This is our macro goal, so to speak. And the second goal is to understand the 3 methods that do all the magical work behind the scenes: rejection sampling, inverse transform sampling, and other statistical transformations. This is our micro goal. Let's take the standard normal distribution for a moment. When we sampled from it, why did we get 1.68? Why not some other value? Why not minus 0.74 or 3.27? In order to answer these questions, we'll have to look under the hood of the algorithm generating the standard normal random variables, a simplified version of it. And we want to look at it in reverse. In particular, we're interested in identifying the first observation of 1.68 and then in looking at the process that generated it. The first thing that happened was that the PRNG randomly sampled the value 0.27 from the standard uniform distribution. That value was converted to an integer in the inclusive 0 to 5 range, used to determine the one rectangle out of the 6 equal area rectangles covering the positive half of the standard normal. Choosing rectangle R1 can be thought of as a low-resolution random y-coordinate. Then the PRNG produced a value of 0.77. That value was multiplied by 2.18, the x-coordinate of the right end of the R1 rectangle, to obtain 1.68, the value we're interested in. And because 1.68 is less than 1.78, we can take a shortcut. We don't even need to sample a higher resolution y value, so to speak, because the entire area within R1 that is to the left of 1.78 is within the green except area. Put differently, the entire area within R1 to the left of 1.78 is outside the red reject region. Finally, the PRNG produced a value of 0.38. Because that value is less than 0.5, our accepted value of 1.68 is kept as opposed to being multiplied by -1, which would mimic sampling from the negative side of the standard normal. And that's it. We are done sampling from the standard normal. The method we just looked at is a simplified version of the ziggurat algorithm, which is a particular flavor of the rejection sampling method. We'll look at it in much greater detail later in the video. Recall that in our aquatic ecosystem analogy, the standard normal distribution is zooplankton, and it eats only phytoplankton that are the standard uniform random variables. We just had a glimpse of how a standard normal random variable is generated using the ziggurat algorithm. Random variables from two other distributions in the core group are also generated using the ziggurat algorithm. As mentioned, the ziggurat algorithm is a type of rejection sampling, and there are two more distributions, the beta and von Mises distributions, that are also sampled using rejection sampling, but using other flavors of rejection sampling. This is where I should mention that many distributions are sampled using a combination of methods. For example, in sampling the standard normal with the ziggurat algorithm, most of the sampling is done by the rejection method. But when sampling from the tails of the distribution, inverse transform sampling also has a small role to play. In my classification, I will say that a distribution is sampled using rejection sampling if it primarily uses rejection sampling. It might be the case that inverse transform sampling or other statistical transformations are also used to a lesser extent. And that's it for the numpy distributions that use rejection sampling. But interestingly, not according to ChatGPT. ChatGPT is convinced that the Wald distribution is also sampled using rejection sampling. But that is not the case. The Wald distribution is sampled using a stochastic statistical transformation, which is somewhat of a strange beast. I will explain what that is a little later in the video. Next, we ask how is it that the sampling from the Cauchy distribution takes place. And this one is a bit easier. I will bring back a snippet of our ecosystem plot showing that the Cauchy random variables can be produced with nothing other than standard normal random variables. In our case, since we are looking to sample from the Cauchy 0,1 distribution, which by definition is a ratio of two independent standard normals, our recipe is quite simple. We just need to sample two values from the standard normal and divide one by the other, and the ratio will be a random draw from the Cauchy 0,1 distribution. This method is referred to simply as statistical transformation, since that's all it really is. And notice that sampling from the Cauchy distribution did not involve random variables from the standard uniform. Rather, it used members higher up the chain, standard normal random variables in this case. Recall that in our aquatic ecosystem analogy, the Cauchy distribution is a large predator, It does not eat the phytoplankton that are the standard uniform random variables. It eats only the zooplankton that are the standard normal random variables. And that's it for the Cauchy distribution. And finally, we want to ask, how is it that the sampling from the logistic distribution takes place? In order to answer this question, once again we'll have to look under the hood of the algorithm generating the logistic random variables, which is inverse transform sampling. The exact same method is used in both numpy and R, with the only differences between the two attributable to the fact that different PRNGs are used by default. Next, I will animate the R version, since R uses the Mersenne Twister PRNG by default, and that is the one we studied in the last episode. And once again, we want to look at the sampling process in reverse. In particular, we are interested in identifying the first observation of 1.94 and then in looking at the exact process that generated it. And there it is, the 1.94 value we are interested in. We can see that it was obtained by reflecting about the CDF of the logistic distribution, the standard uniform random variable that crystallized into the value 0.485. And how was that 0.485 value obtained? Well, this should be familiar territory because that is what we covered in the last episode, but the short answer is the Mersenne Twister PRNG. In our aquatic analogy, we said that the logistic distribution is small fish, not zooplankton only because it is not a core member, but like zooplankton, it eats the phytoplankton that are the standard uniform random variables, and in the case of the logistic distribution, it eats only phytoplankton. It is time to wrap up our effort of characterizing the distributions by the sampling method used. This is where we left off. Next are 4 distributions that are simply generalized or unstandardized versions of the 4 core distributions. These are all obtained by simply stretching and sliding over the respective standardized distributions. Next are the distributions sampled using inverse transform sampling. All the distributions in blue are sampled using inverse transform sampling. And finally, all the distributions in red are sampled using statistical transformations other than inverse transform sampling or the stretching and sliding transformation we just mentioned. We are almost ready to roll up our sleeves and dive into the math behind each of these methods, starting with inverse transform sampling. Inverse transform sampling stands on the shoulders of an absolutely remarkable property of the uniform distribution, a property known as the universality of the uniform. It says that if, for example, you start by sampling a random variable x from the normal 2-2 distribution, and if you then form another random variable y by plugging x into its own CDF, the new random variable y you will obtain will have the standard uniform distribution. If you pause and think about it, this is quite remarkable. But the truly remarkable thing is the absolute generality of this result. X can come from any distribution whatsoever, you name it. But after plugging it into its own CDF, we always end up with the standard uniform random variable. This is nothing short of incredible. We are now ready to roll up our sleeves and dive into each of the three methods one at a time, and we will start with inverse transform sampling.